In this video, we will learn about properties of matrices. Recall that in the last video, we have talked about addition of matrices and multiplication of matrices. Now in this video, we will learn about properties of matrices with respect to addition and multiplication. So I divide the board into half, and in this half we will talk about addition, and this half we will talk about multiplication. So now let's divide the board into kind of half. Now this half is about addition properties. So I write here addition. So the property number 1 that we have to discuss with regards to addition is commutative. The commutative property is about order of matrices. That means I can say A plus B, and if the result is same, if I change the order, if I say B plus A, and if the result is same, then we say that addition is commutative. And yes, addition is commutative. By changing the order of addition, the results remains the same. So we can say that A plus B is equals to what?
B plus A.
B plus A. So that means addition is commutative. The second property we want to talk about is associative. Once again, we are talking about properties with respect to addition operation. Now, associative property is about brackets. That means if we are adding, let's say, 4 or 5 matrices or 3 matrices, how can we place brackets that we prioritize different addition, different order? The result will remain the same. So that means, for example, if I'm adding A plus B plus C. Now, plus operator can add only 2 matrices. So I can choose that I will first add A and B, and then in the result I will add C. In this case, I will place brackets with A and B. But I have another choice, which is that I will first add B and C, and then whatever the result is, I will add that result in A. In this case, where I will place my brackets?
B and B plus C.
Yeah, so I will say first B plus C, and then whatever the result is, add A. In case of addition, we have this associativity property. That means by changing the order of brackets, the result remains the same. We can also use this property for more than 3 matrices. We can use 4 matrices or 5 matrices, and we can place brackets wherever we like, and the order of the placement of brackets will not change the result.
Can we put the brackets in A plus C?
No, A plus C we can't. We can only place brackets with consecutive matrices. Like we can say, either we can add A and B, and then in the result we can add C. Now let's quickly do the 4 matrices example to make the concept clear. So we have A plus B plus C plus D, and we have here also another order maybe. We can in case of 3 matrices there are only 2 possibilities. In case of 4 matrices, there are more than 2 possibilities, but we are only going to explore 2 possibilities. So there are more than 2 possibilities of how can we place brackets, but we are not going to explore all those possibilities. So one possibility here is that we add A plus B first, then whatever the result is, we add C plus D, and then we add both of them. So first we say do this, right? Second we say do this, and third we can add both of them. We can also place another bracket here, but that is useless because this is the last possibility, right? In this case we can say first maybe add B and C, right? Then maybe whatever the result here, add with A. So we'll place another bracket here, right? So we first add B and C, and then we add A in the result, and then at the end, whatever the result we have here, we add with D, right? So can you tell me another property, another sequence of brackets because in case of 4 matrices, we can add in many different ways. So let's say once again I have A plus B plus C plus D. Tell me another order of.
We can put C plus D in brackets.
So C plus D in brackets.
And the answer of that we can plus it with B.
So now whatever the answer we have here, we add that answer with B. And then whatever the result we have here, we add with A. So now because addition is associative, so these 3 are different operations with respect to addition. They are adding different matrices in different ways, but our result will remain the same. So associative is about order of brackets, and commutative is about the order of matrices. So is it clear?
Yes.
So now let's continue. So the third property is about identity. So identity is a special matrix. If I add that matrix, then my results remains the same. That means if I add in A, my special matrix, I call that matrix O. We can call the matrix anything, but I call that matrix O. If I add in A, my special matrix O, my result remains A. So addition has not changed my result. Such a matrix O in this case is called identity. Identity is not different for all the matrices. It must be same for all the matrices. Like for example, if I choose a different matrix B of the same dimension and I add O of the same dimension, my result will be once again B. So question can be asked, or question must be asked, that what is the special matrix O? So any suggestions?
Zeros.
So the special matrix O has all zeros in it. So if I add in A all zeros, my result will be A. So assume that my matrix A is, my matrix A will be A, B, C, D, and O matrix, which is not O matrix, it has a special name. Its name is null matrix, or its name is zero matrix. So this matrix O has a special name, we can call it null matrix, or we can call it a zero matrix. So in A, I add null matrix, which is what? Null matrix will be different for every dimension because I'm in 2 by 2 dimension. So my null matrix will also be 2 by 2 dimension, because in case of addition, we can only add matrices with the same dimension. Remember, in case of addition, we can add matrices with the same dimension. So now I add here 0, 0, 0, 0, and this is what matrix?
Null.
Or?
0.
0. And my result will be what? Because I say A plus 0 and I will have A, I will say B plus 0, I will have B, and C plus 0, C, and D plus 0, D. So my result remains unchanged. So this is another property which is identity property, and this property exists for all the matrices with respect to addition. So last property is inverse property. So the last property of matrix addition, maybe second last property, is inverse property. Inverse means that if I add in a matrix A, a special matrix with respect to A, which I call maybe B, then my result is identity matrix or null matrix in this case, right? So my result is null matrix. Similarly, if I add in, let's say, C, a special matrix D, then my result will be once again what?
Null matrix.
Null matrix. So we can say that B is inverse of what?
A.
And D is inverse of what?
C.
C. Now what will be the inverse in case of addition? That means if I add a matrix in A and all the numbers in A become 0. So what could be the inverse of A? Let's say A has A, B, C, D in it. Then what will be the content of B?
Minus A, minus B, minus C, minus D.
Very good, very good. So the A content will be the content of the matrix B will be the same as the content of matrix A, but the sign of the content will be different. Every entry will have different sign. So if we have here plus A, we will have here minus A. Let's say I have here minus B.
Then be A plus B and then minus C minus D.
Right? So that means we can say that our inverse matrix will be like this. We can write like this. We can say if we have A, then our inverse matrix is going to be minus A. That means we will multiply with minus all the entries of A. This is a scalar multiplication. And our result will be null. If our matrix is B, then our result will be, our inverse will be what matrix?
Minus B.
Minus B. So it is easy to see that for all the matrices we can find inverse, because we can take we can multiply all the matrices with the minus sign. So for all the matrices, in case of addition, inverse exists, right? And it's very easy to find inverse. You can just multiply all the entry with the minus sign, right? So now the last property. So the last property that we want to discuss is closure property. Closure property implies that, let's say we have a matrix A which has a dimension of n by n. That means it has n rows and n columns, and we add it in another matrix B. Obviously for addition the dimensions should be the same. So we add it in another matrix B. Let's say it will also have n rows and n columns. Then our answer will be C, and C will also have the same dimension. So that means if we have matrix which is scale matrix of n by n dimension, then we add two scale matrix and our answer will also be a scale matrix of n by n dimension. So our answer will also be n by n dimension. So that is it for the additive properties. Now we have to repeat the same properties and we have to see if these properties exist for the multiplication operation. So here we have these 5 properties. Number 1 was commutative. Second way we change the order of matrices. Second was associative, where we don't change the order but we change the brackets. Third was identity, and fourth was inverse, and fifth was closure. We have to see if these same properties exist in case of multiplication. So now let's start. So here we have multiplication. So property number 1 is commutative. So in general, for multiplication, this property does not hold. That means in general, if we say A times B, I'm writing here a dot sign, but in case of multiplication you don't have to write dot sign, you can just write AB. So A times B is in general not equals to B times A. That means if we change the order of matrices, our result also change. So commutative property in case of multiplication does not exist. But it doesn't mean that this is always true. And for some special cases, if we change the order, the result does not change. But this property is not true in general. It will not true always. Sometimes it can be true. So this property does not hold. Second property that we have is associativity. And associativity was about
changing the brackets.
So associativity was about changing the brackets. So associativity. And this property holds also in case of multiplication. Let's say we have matrices A, we say B and C. We can maybe first multiply B with C, and whatever the result we have, we multiply with A. Or we can also say that first I will multiply A with B, and whatever the result I have, I will multiply with C. As long as we are not changing the order of these matrices, our result will remain the same. So associative property holds in case of multiplication. So the third property that we have discussed in case of addition was identity property. And we say in case of addition, our identity matrix is what? Our identity matrix.
Null matrix.
Our identity matrix was null matrix. In case of multiplication, our identity matrix is a special matrix. So an identity matrix exists also in case of multiplication. So we can always find identity matrix for multiplication. So identity, that means we have A and we times A with a special matrix which I will call I. And in case of multiplication, everybody calls this matrix I, which is identity matrix. Okay, so we can my identity matrix I, and my answer will be what?
A.
So my answer will remain unchanged. Now this identity matrix is a matrix which is a diagonal matrix. That means it has known zero entries only in its main diagonal, and all of those entries in the main diagonal are ones. That means if I have to write identity matrix, let's say for 2 by 2, so my A is like A, B, C, D once again, then my identity matrix will be a matrix which has all zeros but in diagonal. This is a diagonal. So it will have 1 here and 1 here, and rest of the entries will be 0. So now let's try and see if my answer comes out to be A. How I multiply this with this, right? So I multiply A with 1 plus B with 0, and my answer is going to be what? A with 1 will be A, B with 0 will be 0. So I will say A plus 0, which will be equal to what?
A.
So my answer is going to be A. Similarly, I take this row and multiply with this column. So I say A with 0, answer will be
0.
Plus B with 1.
B.
So 0 plus B is equals to
B.
B. Similarly, I will take this row and now multiply with this column, and when I multiply with this column, I will have C with 1 and B with 0. I will add those 0 plus C, and my answer is going to be C. Similarly, when I multiply this row with this column, I will say C with 0, it will be 0, plus D with 1, it will be D. So 0 plus D is going to be D. So this is my identity matrix for 2 by 2 matrices, right? So I can also find identity matrix for 3 by 3 matrices, which will be once again that its diagonal will have all ones. This is a diagonal entry, and rest of the entries of the matrix will be 0. So this was the identity matrix for 2 by 2 matrices. Similarly, we can write identity matrix for 3 by 3 dimension of matrices. We can write identity matrix for 4 by 4 dimensional matrices. The pattern will remain the same. That means identity matrix will be a diagonal matrix. Diagonal matrix is a matrix which has all zeros except diagonal. And in this case, its diagonal will only have ones in it, right? So now let's quickly write identity matrix for 3 by 3 matrices, just to make sure that everything is clear. So for 3 by 3, our identity matrix is going to be, once again, it's a scale matrix, so it will have 3 by 3 is like 9 entries. So we'll have diagonal have all ones, and then we have 0, 0, 0, 0, 0, 0. So it has 3 rows and 3 columns, and only diagonals have 1. If we multiply any 3 by 3 matrix with this identity matrix, our result is going to be the same matrix, because identity matrix does not change the result. Multiplication with identity matrix does not change the result. So the second last property is inverse of a matrix. And this is extremely important property for multiplication. We are finding inverse of a matrix for many different applications. And finding inverse of a matrix is not a straightforward process. And we have to make a separate video for only how to find inverse of a matrix. So the fourth property is inverse property. Now, once again, this property does not exist for all the matrices. So for all the matrices, you cannot find inverse. But for some of the matrices, you can find inverse. So there are some matrices for that you cannot find inverse. So inverse in this case is called, let's say, A inverse. This is how we represent inverse in case of multiplication. And our answer will be what? If the inverse exists, our answer will be what?
Null matrix.
No, null matrix was in case of addition. In case of multiplication, our identity matrix is called identity matrix. It is not a null matrix, right? So our answer is going to be identity matrix. And this does not exist always. So I cannot find inverse of all the matrices. I can find inverse of some of the matrices. So this property does not exist in general. So this property does not exist in general. In case of addition, these properties always exist. I can always find inverse, which is simply the negative of that matrix. But in case of multiplication, finding inverse is complicated. I will have a separate lecture in which I will explain how to find inverse of a matrix, and we can find inverse only sometimes, not always. So not always, right? So not always. Similarly, this property exists sometimes, but not always. This property is also not always. Sometimes it exists. So last, the fifth one is like closure. That means if I have matrix A, and let's say A has dimension of n by n, and I multiply with matrix B, and B also has dimension n by n, then my result will be C, and C will also have dimension of n by n. So closure property exists in case of multiplication also.